Hello and welcome to a Maths with Harry lesson. In this video, we're going to have a look at modelling with straight lines. Now, first of all, we need to think, what is a mathematical model? Okay, we're going to look at straight lines in this video, but let's just have an overview of what a mathematical model is. We don't do too much modelling in this pure course because what we do really is we get onto the mechanics later on in the end of the first year, and we do quite a lot of modelling there. But we're going to introduce modelling here just with straight lines. Now, the definition is a mathematical model is and let's get rid of that, an attempt to represent a real life situation using mathematical concepts. Okay, so two key words there, three really. We've got attempt and we've got mathematical concepts. What we do when we model something is we take a real life situation and we attempt to model that real life situation using mathematics. Okay, so when you get onto mechanics, you might see or you will see a ball being thrown in the air. Okay, that's a real life situation. You'll have a person throwing a ball, and you can take that situation, it's a real life situation, and you can model that using maths. Here we're just looking at straight lines, so we're not looking at that. When you get onto mechanics, that's what you look at, okay? And it's an attempt because we often have to make assumptions. We can't get the model completely accurate, okay? We can only attempt to model the real life situation. So we have to make assumptions along the way, okay? And we make more assumptions in mechanics. We're just having a look at straight lines here. So before we do anything, we need to know what direct proportion is. And it says on screen here, direct proportion, or two things, are in direct proportion if they increase at the same rate. So, for example, you might have heard the example maybe at GCSE, direct proportion. Two things increase at the same rate. An example of that would be if the temperature increases, then the number of ice creams increase, okay? Or the number of ice creams sold. If it is hotter, the temperature increases, so more people are going to want to buy an ice cream. Or you could think as the temperature increases, the number of bottles of what's it called? Sun cream, that's the word. More sun cream is going to be sold, okay? So we can have a look at direct proportion on a situation like that. Now, direct proportion like this, the graphs of these quantities, is just a straight line through the origin, okay? You can think, if we've got, for example, if I draw an axis, and we've got one here actually, if, for example, I'll do this in blue, this was the number of ice creams sold, and the temperature, we can see that's just a straight line through the origin, okay? They're directly proportional to each other. As the number of ice creams sold increases, the temperature also increases as well, because we can follow this straight line here, okay? And it's a straight line through the origin, but it has some kind of multiple out the side of it. It might not be exactly y equals x. It could be y equals some multiple of x, but they always pass through the origin, okay? Now, let's just have a look at some notation. So all of these things mean the same thing, and I'm going to show you three ways of writing proportion. So y is proportional to x is the same thing as writing this. Y is proportional to x, okay? This kind of looks similar to this x. They're different things. This is an x, this is proportional to. So y is proportional to x. And then the third thing is, well, we've got this example like we've already seen. Y is equal to some multiple of x. In other words, it's a straight line that passes through the origin, okay? And I'll just specify here where k is some real constant. Okay, so those are three ways of writing proportion. So direct proportion, two things increase at the same rate. The quantities graph a straight line passing through the origin, and those are three ways of writing proportion. Okay, we're going to have a look at two examples, just taken from the textbook here. So this is a screenshot of the graph. And it says the graph shows the extension E of a spring when different masses M are attached to the end of the spring. So say, for example, this pencil is a spring. Okay, spring can open and close, or sort of extend and descend, if you like, or stretch, and we add some weights on the end. You can see if you add weights, the spring is going to stretch, okay, and then if you let go of the weight or take the weight off, the spring will go back up, okay. So that's what we've got going on here, and we're adding different masses to the end of the spring. And we can see, just by looking here, we've got direct proportion, because we've got a straight line, and the straight line passes through the origin. So the mass on the spring and the extension of the spring are directly related. We're not even going to ask or have a look at what the question is asking us. Let's just consider direct proportion for these two things. We've got a straight line, so that's good, and I just said it passes through the origin, so that's good. And then we can see, as the mass of the spring increases as we go this way, okay, we can clearly see that, well, let's have a look at the line. The line is also increasing, so that means the extension of the spring also increases, okay, and that makes sense. If I've got a spring and I add a tiny little weight on the end, it's not going to extend the spring that much. But if I add a big weight, or I pull down on the spring that's much heavier than the little one I've just added, we can clearly see that's going to pull the spring a lot further. The extension of the spring is going to be a lot larger. And that's exactly what we've got going on here. A mass of 400 grams, okay, extends the spring to a length of 20 centimetres. Okay, so that's the extension of the spring. But if we look at a mass of 100, we can clearly see the extension of the spring is 5 centimetres. And so direct proportion says the heavier the weight, so as the weight or the mass of the weight increases, then the extension of the spring also increases. So they're increasing at the same rate. We've got direct proportion. Okay, so we've got three things for this question. We want to calculate the gradients, we've called that K of the straight line. We want to write an equation linking E and M. And we want to explain what the value of K represents in this situation. So you might be able to have a go at A and B. This is a real life situation we're modelling here because we've got a mass and we've got a spring. We're doing something in real life. We're not just being asked to find the gradient of this straight line. We're using our knowledge of straight lines to help us with a real life situation. C you might not be able to do. You might want to wait for me to do that, but pause and have a go nevertheless, and then press play and we'll work through the answer. Okay, let's have a go at part A. So quite easy, we're just wanting to calculate the gradient. Pick 2 points on the straight line and just calculate the gradient. So part A, I'm going to pick 2 points here, and I'm going to pick 2 nice points, to be honest. I think, well, 0, 0, we'll do it in a different colour. 0, 0 will be a great point to pick because it passes through 0, 0. And when we take away 0, it's just no difference, so that's a good point. And another point that I could choose is, I don't know, this point here, or to be honest, the point at 300 grams, or the point at 20, or the point at 100, okay? Doesn't really matter. I will, I'll do the points at, in fact, let's see what the book does, so we can do the same as that. It picks the point I was going to pick, actually, at 420. So we'll pick this point here, and that point there. Okay, so that point is a mass of 400 and an extension of 20. And then there, of course, is the origin, so it's at 0, 0. So to work out the gradient, all we're going to do is take those 2 points, find the change in y, find the change in x, and divide them. So the change in y, we can clearly see. Gradients is what I'm working out here, and we've called that k. The change in y we can clearly see is 20 minus 0, okay? And then we're going to divide that by the change in x. So divide by 400 minus 0, okay? Don't need the negative zeros, so they will just disappear, making no difference. We can cancel down by 10 to give me 2 over 40, which will give me 1 over 20. So that's the gradient of the straight line. And we can see that because if it had a gradient of 1, it would look something like that green line there. And we can clearly see, maybe a little bit more like that actually. We can clearly see it's a lot, that line is a lot steeper than the line that we're drawing here. So it's got to have a gradient less than 1, which exactly it does. It's got 1 over 20. Okay, so that's the gradient of the straight line. We'll highlight that in yellow, and that's our value for k. Now what we want to do is we want to write an equation linking E and M, okay? M is the mass of the spring. We can see here, we're told that M is the mass of the spring, and E is the extension of the spring. So we want to basically have E equals something in terms of M. So all we've really been asked to do is find the equation of the straight line. Now that's quite simple, okay? Y equals mx plus c is our general straight line, if you want to think about it like that. But here we've not got y and we've not got x, we've got E and M. We pass through the origin, so the y-intercept is 0. So all we're going to have is y equals the gradient times x, but it's not y and x, it's E and M. So what we're going to have is this, okay? E is equal to some multiple, which is the gradient, times the mass, our x-axis, M, there's our y-axis, which is E, plus the y-intercept, okay? We'll just call that C. Okay, well we know the y-intercept is 0, so we're just going to have E is equal to some multiple times M, and then we know what K is, it's the gradient, so 1 over 20 M. So in other words, we're just being asked to find the equation of the straight line. Also, that is one of the forms of expressing direct proportion, okay? Y is equal to some multiple of x. And again, here we've not got y and x, we've got E and M. And that is the equation linking E and M together. We've got E expressed in terms of M. So that is our final answer for B, okay? So C says, explain what the value of K represents in this situation. So we always have the same answer to this. E is equal to some multiple of M, okay? And that multiple is 1 over 20. So what does K represent? Remember, this is K, okay? Well, if we think about it, let's set M equal to 1, okay? So let's just put a little consider first, okay? Set M equal to 1. If we set M equal to 1, that tells us that E will be 1 over 20. That's the extension, okay? So as the mass increases by 1, the extension of the spring increases by 1 over 20. And the book says here, K represents the increase in extension in centimetres when the mass increases by 1 gram. Because if we set the mass to be 1, we've got an extension of 1 over 20. So every time we increase by 1 gram, the extension increases by 1 over 20 centimetres. So I'll just copy from the book. It says K, or in other words, K equals 1 over 20, represents the increase, and don't forget your units here because it's a real life situation, in extension in centimetres when the mass increases by 1 centimetre. Okay, and that's kind of always the case. Whenever you've got an equation like this, okay, as this variable here increases by 1, we saw it here with the maths, the extension, or whatever the variability, here we've got extension, increases by 1 over 20. Okay, Right, let's have a look at another example. This is the final example for this video. It says a container was filled with water. A hole was made at the bottom of the container and the depth of the water remaining was recorded at certain time intervals. And then we've put the results in the table. So we can see at these different times here, we filled a container with water, we put a hole in and measured at, well, 0 seconds, 10 seconds, all the way till 120 seconds, the amount of water left in the container. Because of course, if we put a hole in the container, the water's going to drip out. So we can see the depth of water at 0 seconds was 19.1. The depth of the water at 10 seconds in centimetres was 17.8. All the way to after 120 seconds, the depth of the water was 3.5. We've got 4 questions here. It says, is a linear model appropriate? Part B says deduce an equation in the form D is equal to AT plus B. What are the values, or what are the, not the values, the meaning of A and B? You'll find the values of A and B in part B. And then D says use the model to find when the container will be empty. So, real life situation, use what you know from the maths and apply that, make some assumptions if you need to, and then we'll work through the answer. So pause and have a go, and then press play when you're ready. Okay, let's see what we can do. So part A, all we have to do is test whether a linear model is appropriate. Remember, linear just means straight line. A linear set of simultaneous equations is when we've got two things in the form y equals mx plus c, okay? Linear just means the highest value of our variable, in this case x, is 1. So, let's have a look. All we have to do is just graph these things here. That set, that set, that set. We just have to graph those as coordinates, okay? We put the time along the x-axis because it's time and that's t, we call it the t-axis. And then we put the depth of water along the y-axis, but because it's depth of water, we'll just call it the d-axis, okay? So that's all we need to do. We just draw those points on. So we can see this point here, 0 and 19.1. Well, 0 time 19.1 is about there. Now, of course, you don't have to get this perfect. If I was reading this without the coordinate, we've got that from the table, that is 0, 19.1. I'd probably say that's 0, 19, but because we know that's the coordinate from the table, we can take that there, okay? That's then the next coordinate at the time, what was it? Is that 10? Yes, it is. It's halfway between 0 and 20, so that's at time t at 10 seconds. And then all the way down here, we've got 120 seconds. We have got something like 5 point something, is that? Oh no, 3.5, of course, because it's below 4, okay? So that's what we have to do for part A, and I've just took that just from the book to speed some time. Okay, part B says deduce an equation in the form D is equal to AT plus B. When we've got the word deduce, all we need to do is just find the equation in the straight line. Use the maths and find the equation, okay? We can see it's a straight line equation, so just find the equation of this straight line, okay? We're going to take 2 points to work out the gradient, and the 2 points I'm going to take is this point here, that coordinate there. I'll highlight it in yellow, just to make it easy because it's at the x point of 0. So I can take away 0 and that's not too hard to work out. And I'm also going to use this point here at, and I'll draw it on, we're going down here to 100 and we're going across to about 6.1, I think, on the table, 106.1, yeah. So we've got an x-coordinate of 100 and a y-coordinate of 6.1. Those are 2 points on the straight line. We can use those 2 points to find the gradient. So let's do that first. The gradient is going to be the change in y. The change in y, we can see the line is going down here, so we're going to get a negative. And the change in y is we'll take this point and we'll take away this point. So 19.1 minus 6.1. 19.1 minus 6.1 divided by the change in x. We've gone from 0 to 100, so 0 minus 100. You could have also done it the other way around. You could have said 6.1 minus 19.1. So this coordinate take away this coordinate, doesn't matter as long as you keep it the same. Divided by 100 take away 0 would have given you the same answer, and we'll take it from the book, is minus 0.13. Okay, so that is the gradient. I won't highlight it in yellow actually because it's not the answer. I'll highlight it in grey. We're going to need that in a minute. So, equation of a straight line, remember, is y is equal to mx plus c, but in this case we've not got y and x, we have got t and d, so it's going to be d is equal to some multiple of t plus c. C is the y-intercept, m is the gradient, so we know it's going to be d is equal to minus 0.13 t plus the y-intercept, and we can see from this point here on the x-axis, the straight line intersects at this point here, which has a y-coordinate of 19.1. So C is going to be positive 19.1. And that then is our final answer. Okay? We've got the equation, D is equal to minus 0.13t plus 19.1. This is, I'll do it in a different colour, this is our A value, and this is our B value, just comparing it to what we were asked to find in the question. Okay, so C says interpret the meaning of A and B. A is the change in depth of water in the container every second, okay? Just like the other question. If we were to change our time, if we were to set time to be equal to 1, ignoring this value just for a minute, we can see the depth of water will decrease by 0.13 centimetres. Is it centimetres? Yes, I think it is. Centimetres, yes, okay. So as we increase by 1 second, the depth of water is decreasing by 0.13 centimetres, or increasing by a negative depth, okay. So I'll write that here. A is the, and I'll just bullet point it, A is the change in depth of water in centimetres every second. Okay, and it's the water in the container. And then B, if we think about it, how can we just get B on its own? Well, we can get B on its own just by, on this side, setting T equal to 0, okay? How can we get D being equal to just 19.1? That's when T is equal to 0. And we know that from this coordinate here, at time T equals 0, our depth in the water, or in the container, is 19.1. And so B is the depth of the water in the container at the beginning of the experiment, okay, at the beginning of this situation. We hadn't started the time, T was 0, so that was the initial depth of the water. Initial being at the start. So B is the initial depth of the water in centimetres at the start of the experiment. Okay, so hopefully that makes sense. This gradient, the A value, is always the, well, in this case, in this situation, is the change in depth of water in centimetres every second. So as this value increases by 1, D increases, or in this case decreases, by this value here. And B is the initial depth. If T is 0 at the start of the experiment, the time is 0. The depth of the water is the value B, so B is the initial depth of water in centimetres at the start of the experiment. Part D says use the model to find the time when the container will be empty. When the container will be empty, think about what that means. that means there'll be no water in the container. The container's empty, so all the water has come out of the hole. So that means the depth of the water in the container must be 0. So we can write that here. Depth of water will be equal to 0 centimetres, because that will make the container empty. So let's set, remember that is D, let's set D equal to 0 in this equation. So D is equal to minus 0.13t plus 19.1. Set D equal to 0, we'll get this. And then what can we do with that? Well, it says find the time when the container will be empty. So we're just going to solve for t. I'm going to add minus 0.13t to both sides to give me 0.13t is equal to 19.1. Then I'm going to divide by 0.13 to give me t on its own, and that will give me 146.9. So that's my value of t. But remember, we are dealing with a real life situation. So what does that mean? Well, t is in seconds. So let's write seconds on there. And then it's always useful to do a little statement. So we could say it will take 146.9 seconds for the container to empty. In other words, it will take 146.9 seconds for all the water to fall out of the container.